All right, so we're going to look at inverse circular functions and their derivatives. So some prior knowledge, circular functions, need to have a pretty solid understanding of that. Inverse circular functions, differentiation, and then the derivative of the inverse sine function. If you've seen that video that I made before, it'll help with this, but we will go through that again, but for cosine this time. So the key concepts that we'll cover in this is the derivative of the inverse circular functions review. So just sort of a quick demonstration of the different derivatives of circular functions. Then we'll do a proof of the derivative of inverse circular functions when there's dilations from the y-axis. And then we'll look at inverse sine function derivative, inverse cosine function derivative, inverse tan function derivative. And then we'll look at an application, because you're probably wondering when on earth would you use these kinds of functions. And the example will be sort of drones. So that'll be interesting. So let's jump into it. If we look at the inverse sine function and its derivative, what we have in pink here, if you just look at pink, is the graph of sine x between negative pi on 2 and pi on 2. And so that's just our ordinary sine of x graph, but we've cut it off to make it a one-to-one function, because we need to start doing all these sort of taking the inverse and differentiating and all that. So we need to cut it off between negative pi on 2 and pi on 2. And so as I change this slider, if we just look at the pink one for now, it'll turn it into its inverse sine of x. And remember, the inverse function is a reflection in the line y equals x. So if you just look at the pink line for now, you'll see that you'll get something like that. And it actually goes between negative 1 and positive 1 now. And remember, that's because all the x and y values have changed. So if you think about your sine of x graph, the left endpoint is negative pi on 2, negative 1. So that becomes negative 1, negative pi on 2 as your sort of left endpoint for your sine inverse graph. Okay, and so what we can see as well is if we go back now and start investigating this blue line, well, hopefully you would agree that the derivative of sine is cosine, and this is the start of the cosine graph. So it looks something like this. And then you can see, we've spoken about before, but the derivative of the inverse sine is this graph looking here. Okay, it sort of looks like this. And we've spoken about that before a little bit, but we'll talk more in detail about where that comes from. But that's what the graph looks like. And again, just getting a feel for the derivative. Down here, near x equals negative 1, you'd have really large positive tangents. So you're getting really large positive values near x equals negative 1. And similarly, you get really large positive values when x is close to positive 1. So yeah, and just don't look too much into how these graphs are transformed from one to the other. Like that's definitely, the blue line is definitely the derivative of the inverse function, but like in between, I'm not sure the mapping is exactly graphing the derivative, but that's certainly the derivative of sine x in blue, and that's the derivative of sine inverse of x once we've moved the slider the whole way. I'm just sort of saying don't look too much into the way that it's being transformed. And every point along the way is not the derivative of the graph as it's being sort of shifted, is what I'm trying to say. All right. Let's do the same thing for inverse cosine function. So again, cosine we've now got in pink, and we're going to transform it to the inverse of cosine. So that's going to look like this, which should hopefully be a review. This graph here is the inverse cosine. And yeah, if we go back again, we can see that the derivative of cosine is negative sine, which is what we've got in blue here. And then that's going to be transformed to the derivative of cosine inverse. And so this is negative sine, and then this is the derivative of inverse cosine. And again, we're getting bounds between negative 1 and positive 1. I've just got radians on this axis here, but that's the same thing. These values are at x equals positive 1 and x equals negative 1. Okay, final demonstration is inverse tangent function and its derivative. So again, in pink, we've got the tan function. We're just looking between negative pi on 2 and pi on 2 at the moment. And let's just watch this transform. So we're going to reflect it across the green line, y equals x. And so the pink line looks like that. So that this pink line now is the inverse of tan. And if we take it back, This graph here is the derivative of tan. As we transform it, it becomes the derivative of tan inverse of x, which looks like this. Which looks kind of nice, I think. Looks like a bit of a bell curve, doesn't it? So I think that's interesting. Okay, we're going to talk in more detail about what these sort of blue functions actually are. So let's look at that. We're going to look at an example for cosine. So it might be worth getting a pen and paper out here just to work through this derivative proof. But the way we're going to do it is by using the inverse function idea, where you take the inverse derivative. So let me explain. So if we've got y equals cosine inverse of x on a, so remember that x over a represents a dilation by a factor of a from the y-axis. And so if we take cosine of both sides, we're going to get cosine y equals x on a, just by doing the same thing to both sides. So then, by just rearranging, we get x equals a cosine y. All right, now differentiate both sides with respect to y. So we're actually finding dx dy. Okay, that's going to give you, well, the derivative of cosine is negative sine, so it's going to be negative a sine y. So the reciprocal rule says that dy dx is equal to 1 over dx dy, and we know dx dy, which is this. So we know that dy dx is 1 over negative a sine y. And so we get, we get dy dx is negative 1 over a, we just move the negative up the top. And since cosine of y is equal to x on a from over here, we can use that sine squared y equals 1 minus cos squared y. Okay, so if you rearrange that so I should say this is the Pythagorean identity. If you rearrange that for sine y, you'll get sine y equals the square root of 1 minus cos squared y, which we had here, but cos squared y is x minus a squared. So dy dx is negative 1 over a times the square root of 1 minus x minus a squared. So there's our answer, there's our final answer. Now, sometimes you'll see it like this, negative 1 over the square root of a squared minus x squared, which is probably a little bit neater. But the reason you can do that is because you can take this first a as being the square root of a squared and then put it inside there. So it becomes negative 1 over the square root of a squared minus x squared, because when you multiply that into there, the a cancels out. Okay, so definitely make sure you've wrapped your head around that in terms of how we got there. And I'll put a link below for that reciprocal rule video, which we sort of spoke about. And here's another proof. I won't talk through this one, but pause the screen and have a look. This is obviously getting the same result, but just doing a slightly different method, just using the chain rule and using some implicit differentiation stuff. So certainly important to understand things in multiple ways. So I would recommend having a look at that and making some sense of it. All right, what we're going to do now is just going to run through the derivative rules for sine, cosine, and tan. So here it is. So we say that the inverse sine function derivative for some function f that goes between negative a and positive a, and the function is inverse sine of x on a, then f dash is equal to SGN of a. I actually don't know how to say this. Sometimes you see it on the calculator. I'll explain what it is in a second. Over the square root of a squared minus x squared. So that's what we said before. And remember, a is this dilation factor from the y-axis. So if a is 2, for example, then it's a dilation by a factor of 2 from the y-axis. So this SGN of a business is basically saying if a is, it's saying that if the numerator will be 1 if a is greater than 0, and the numerator will be negative 1 if a is less than 0. So if we pick values of a less than 0, you would agree that the graph would have to flip across the x-axis because you would have negative tangents along this sine inverse function. So it would have to be down here. Now, the specialist course I don't think expects you to understand that. It just takes values of a that are positive, but I thought it's better to fully understand the derivative, because if it's reflected in the y-axis, then the derivative needs to be reflected across the x-axis. So this is what we get. We end up with this situation going on here. And you can see that, again, the sine inverse function, when a is 1, goes between negative 1 and 1. and that corresponds to asymptotes on the derivative function. And yet when a is negative, then this numerator becomes negative. So then we get a reflection of the derivative over here. Okay? Yeah, hopefully that's making some sense. Let's look at the inverse cosine function. Again, inverse cosine function looks like this. Okay, the derivative, just like we spoke about here, is this. And so we get, that the derivative is negative SGN of A, or the sine of A, I think is how we might say it, over the square root of A squared minus X squared. Okay, but we notice that is negative. So if A is positive, then the numerator is negative, which makes sense, because if we have positive A values, then the slope of this line is always negative, so we end up with the derivative that's below the x-axis. So that should make sense. And so it's sort of, and then if A is negative, if A is less than 0, we take this to be negative 1. So we get negative 1, which is positive 1, which is why we end up with the derivative above the x-axis. And so, yeah, pretty interesting stuff. And then, yeah, you can sort of do these transformations to it by dilating it from the y-axis. So, yeah, I think that's pretty interesting. All right, next thing is the tangent. All right. Again, this isn't a proof, but this is the rule. I encourage you to work on the proof, but if you've got some function that's the tan inverse of x on a, then f dash of x, so the derivative, is a on a squared plus x squared. So, yep, what we have here is, in pink, we have the tan inverse function. And then in blue, we've got the derivative of the tan inverse function. And then we can dilate from the y-axis. So if a is 2, it's dilation by a factor of 2 from the y-axis. And it sort of flattens the derivative a little bit. We get this sort of situation going on. Looks kind of cool. If a is negative, let's see what happens. We don't have to have any of this SGN or the sine of a stuff, because if a is negative, this a accounts for it. This a on top accounts for the fact that the whole thing is going to be reflected. The whole derivative, I should say, is going to be reflected across the x-axis. So we end up with a situation like this. Looks pretty cool. Don't look too much into what happens at a equals 0, because then you'd be dividing by 0, so get some wacky stuff going on. But yeah, that's the derivative of the inverse tangent function. All right, so you're probably wondering, when on earth would we use any of this sort of stuff? And I thought, why not do a application? So rise and sine, a drone application. So let's look. So a drone is flying at a constant altitude of 50 meters. An observer on the ground tracks the drone as it moves horizontally. Let x be the horizontal distance from the observer in meters. The angle of elevation is defined as theta of x equals tan inverse of h on x multiplied by 180 on pi. Okay, so there's a bit going on here. 180 on pi, I should just say, is to convert everything to degrees, just because we're more used to thinking about angles sometimes in degrees in more practical applications. Okay, this h is saying it's 50 meters. So you've got some drone, you're looking up at it, it's flying at an altitude of 50 meters. And then x is the horizontal distance between yourself and the drone. So if we look at this diagram down here, imagine you're standing at sort of this end of the triangle, the drone's up here. The horizontal distance will be mapped along the x-axis, and it's flying at an altitude of 50 meters. And the question is, how does the angle of elevation that you're looking at the drone change depending on how far away the drone is from you horizontally? So if you take the derivative of the inverse tan function, which was using the rule that we spoke about over here, you'll get this, or just use your calculator. And then, so the question is, when x equals 50, how fast is the angle changing? So let's really think about this. So we've got this horizontal distance between yourself and the drone being 50 meters, and it's at a height of 50 meters. So if you think about it, you've got an isosceles triangle here. This length here equals this length here. So you must be looking up at an angle of 45 degrees. And that should make sense. So if we look at the original function, remember, theta, the angle you're looking up at, is a function of x, how far away the drone is horizontally. So if you put this to 50, roughly, if I can get it there. I might not be able to. That's close enough to 50 on the original function. You can see that the y value is 45. And that corresponds to 45 degrees. And that should make sense. Again, if the drone's flying at 50 meters high and it's 50 meters away from you horizontally, you must be looking up at an angle of 45 degrees. Okay, but more interestingly, the question says, when x is 50, how fast is the angle changing? And so when we graph the derivative, we get this down here. This is what the derivative graph would be. And so we can see that when x is 50, so when it's 50 meters away, the angle at which you're looking at the drone is decreasing by 0.57 degrees for every meter that it moves horizontally. So yeah, that's what this derivative graph is saying in terms of understanding sort of the practical application. So for every meter it moves horizontally, the angle is changing. It's decreasing by 0.57 degrees. Okay. And so, if we sort of think about that, if we were to lower the height of the that the drone is flying, so we said it was flying at 20 meters high instead, you get a different rate of change of the angle when it's 50 meters away. You're not having to change how much the angle of your head is moving when it's 50 meters away because it's closer to you. So it's only changing at a rate of 0.4 degrees when it's 50 meters away from you horizontally. So yeah, this parameter h changes how high the drone is flying. And to really understand what's going on, we can obviously see some strange behavior at 90 degrees, but that obviously corresponds to the situation where the drone's flying at 50 meters and it's 0 meters away from you horizontally. We're going to have to be looking directly up at the drone because your head can't go to angles of elevation more than 90 degrees. You'd be looking directly up. So yeah, hopefully that drone application sort of shows you an example of when we might use inverse trigonometric functions. And yeah, if you found this video useful, give us a thumbs up. Let us know how you're going. If you need any private tutoring, shoot us an email. And yeah, keen to hear about what you're learning, and I'll talk to you soon.